Hi, I'm Colin, and I'm going to talk to you in this video about Laplace transforms and their usefulness for solving differential equations. So we'll start with the definition of the Laplace transform. We write L of a real function f of t is equal to big F of s, and it's defined as an integral from 0 to infinity e to the negative st f of t. So using that definition, we will be able to find the various Laplace transforms, which is this guy here, f of s, and then that's going to be helpful to solve differential equations. It's going to turn the differential equation into a algebraic equation that we can solve for f of s here, and then we're going to use the fact that we know the inverse of f of s, and it's going to bring us back to f of t. But we're getting ahead of ourselves here with that. So the Laplace transform f of s is defined for piecewise continuous functions that are of exponential order. So functions like e to the t, sine of t, cosine of t, plain old t, t squared, these are exponential order. And that's because they are less than a function of this form for the constants c, m, and t, and this is true for t greater than t, big T. So for any value of these functions, or these constants, this function here is always going to be greater than this one. So something that's not exponential order is a function like this, e to the t squared, because e to the t squared is going to be larger than for any c, m, or t. Okay, so with that in mind, now we know what kind of functions we can use this on. Let's just, I'm going to write something else here. The inverse Laplace transform, something like this, of a function of a complex variable s, is going to take us back to the original function. So that's going to be the final step in using the Laplace transform to solve a differential equation. So that's another thing. I don't know if I set up here. This is a function of a real variable, t, and this is a complex variable, s. But that doesn't really matter for our purposes. So let's do an example of finding a Laplace transform. This is a helpful one. Sine of t is equal to what? So we're just going to use the definition that a Laplace transform of a function is equal to the integral from 0 to infinity e to the minus st, and f of t. So using that definition, we start e to the negative st sine of t, and then we're going to have to use integration by parts for this. So I'm going to write f is equal to e to the negative st dg sine of t. G, therefore, is negative cosine of t, and df is negative s e to the negative st dt. So then we get this. I'm going to call that I. That is equal to negative cosine of t e to minus st from 0 to infinity minus negative cosine of t negative s e to negative st dt. I'm just gonna make these minus signs go away since there's two of them there, and we get I is equal to negative cosine of t e to the negative st from 0 to infinity minus cosine of t s e to the negative st dt. And again, do another integration by parts with f equal to s e to the negative st dg is equal to cosine of t dt. G is equal to sine of t, and df equal to negative s squared e to the negative st dt. So I is equal to negative cosine of t e to the negative st minus s. I'll write sine first. Sine of t s e to the negative st minus again. I'll write this in here. 0 to infinity sine of t, we got negative s squared and e to the negative st dt. So then if I send that minus sign through, I get minus sine s e to the negative st plus, write the, no, that's actually going to be a minus. Got a minus there, so that's going to remain negative. Negative s squared, 0 to infinity, sine of t e to the minus st dt. And then over here we've got negative cosine of t e to negative st. And that is all equal to I. But then this over here, this is also equal to I. So if I add this to both sides, I'm going to get I plus s squared I is equal to negative cosine of t e to the negative st from 0 to infinity minus sine of t s e to negative st from 0 to infinity. So this over here is going to be I1 plus s squared is equal to negative cosine of b e to the negative s b minus cosine of 0 e to the negative s times 0 as b goes to infinity minus, same thing over here, sine of b s e to the negative s b minus sine of 0 s e to the negative s 0 as b goes to infinity. So this is going to go to 0, so we can ignore this whole term. This is going to be 1. This is going to be 1. This is going to be 0, and this is 0 as well. No, I'm sorry, that's not 0. But we don't care what that is, since that's 0. This is going to be 1. And this is going to be 0. So we can just basically ignore this whole thing. And we end up with I1 plus s squared is equal to, we've got a negative here, and negative, so it's just equal to 1. So I, which is our original definition of the Laplace transform, is equal to 1 over s squared plus 1. So you can say from that that the Laplace transform of sine of t is equal to 1 over s squared plus 1. And using a similar method to that, we can also just generally say that the Laplace transform of sine of kt, where k is some constant, is equal to k over s squared plus k squared. So using the definition, you could find all of your Laplace transforms this way for every problem that you had to do, and there's nothing wrong with that. Some of the other ones are a little bit easier, like e to the at. We could do the definition to find that. It's pretty easy, but we can just look it up in our differential equations book, and we know that that is 1 over s minus a. So I'm not going to show all of the steps to find out that this is true, but you know how to do it now, just using the definition. Okay, so how are we going to use the Laplace transform to solve a differential equation? First, we need to know what the Laplace transform of a derivative of a function is. So we can just say that the nth derivative of the function is going to be equal to s to the n big F of s minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0, and then that keeps going all the way until there's no more s's left, and you get to f to the n minus 1, the n minus 1th derivative of f of t. So that's the general form for the transform of a derivative, and that can be found using the definition as well. Using integration by parts. So something like that, we're just going to get s f of s minus f of 0. That's the first derivative. Okay, so let's use that property to solve a differential equation. We're going to start with the equation y prime of t plus 3y of t is equal to 13 sine of 2t. And we're also given the fact that y of 0 is equal to 6. Okay, so what we're going to do is just take the Laplace transform of both sides. And on the left side, it's linear, so we're just going to have y prime of t plus 3y of t. And then over here, we can pull that 13 out, and we just found out the what the Laplace transform of sine of t is with a constant here. So k is equal to 2 in this case, so we have 2 over s squared plus k squared, which is going to be 4. So we'll just write 26. And then over here we have the Laplace transform of the first derivative. So that's going to be s f of s. Since we don't know what this function is, that's what we're trying to find out, y of t. Right now it's an unknown. We've just got s f of s minus f of 0, and then plus 3 f of s. And that's equal to 26 over s squared plus 4. So we will pull out the f of s. That's what we're trying to find in the end. And we get s plus 3. And we know that this is equal to 6. So we'll add that to both sides. And we'll get 26 s squared plus 4 plus 6. And then we'll divide out s plus 3. And we get f of s is equal to 26 over s squared plus 4 s plus 3 plus 6 over s plus 3, which is going to be equal to 6s squared plus 50 over s plus 3 and s squared plus 4. But that doesn't really help us out a whole lot because we don't know of a function that when you take the Laplace transform of some f of t, we don't know of anything that's going to equal 6s squared plus 50 over s plus 3 times s squared plus 4. So we need to get this guy into a different form. And for that we're going to do a partial fraction decomposition. So we're going to write 6s squared plus 50 over s plus 3 and s squared plus 4. This is going to be equal to something over s plus 3 plus something else over s squared plus 4. And then multiplying both sides by s plus 3 times s squared plus 4 gets us to 6s squared plus 50 is equal to as squared plus 4a plus bs times s plus 3 plus c times s plus 3. And that further reduces to as squared plus 4a plus bs squared plus 3bs plus cs plus 3c. That should be a s. 6s squared plus 50. So then equating the coefficients on both sides, we get 6 is equal to a plus b. That's the s squareds. The s's got none on this side. It's equal to 3b plus c. And then we've got 50 is equal to 4a plus 3c. And then rewriting that as a little matrix, we get 1, 1, 0, 6. 4, 0, 3, 50, and 0, 3, 1, 0. And then reducing this matrix down to reduced row echelon form leaves us with 1, 1, 0, 6, 0, 1, negative 3 quarters, and negative 13 halves, and 0, 0, 1, 6. So right away we can see C is equal to 6. And then from that we can find out that B is equal to negative 2 and A is equal to 8. So if you don't really know how to do this, you can just go to wolframalpha.com and plug that in, type partial fractions, and it'll just tell you how to do that. So using these three, we get f of s is equal to 8 over s plus 3 plus, we got negative 2s plus 6 over s squared plus 4. So that came from right here. Just plugging those values of a, b, and c in there. So now we know what f of s is, and it's in a more useful form here. We can find the inverse Laplace transform of this function. So we're just going to do the inverse of both sides. Big F of s is equal to the inverse of 8 over s plus 3 minus the inverse of 2s over s squared plus 4 plus inverse of 6 over s squared plus 4. So this right away, we know what that is. That's just going to be f of t. No, I'm sorry. This is y of s. So this is going to be y of t, which is what we're looking for in the long run here. And then we just have to figure out what each one of these is equal to. So this one looks familiar. If you remember, I wrote a little bit ago that the transform of e to the at is equal to 1 over s minus a. So we've got that form right here. We've just got that extra 8 on the top. So if I just bring that 8 out to the outside, then I've got 1 over s minus a negative 3. So we can see that the function that when taken the transform of brings us to this guy here is going to be 8 times e to the negative 3t. So y of t is equal to 8e to the negative 3t. That's for starters. And then we've got minus, still got these other ones to go, 2s over s squared plus 4 plus 6 over s squared plus 4. So this one looks familiar. We just did that one. That one comes from the sine. But this one has got the s on top. So what do we do with that? Well, using the definition of the Laplace transform, like we did earlier, it can be shown that cosine of kt is going to be equal to s over s squared plus k squared. So we've almost got that here, except we've got this extra s here, or this extra 2. So we're just going to pull the 2 out. I'm going to write 2 L of inverse of s over s squared plus 4. So we can see that our k is going to be equal to 2, and this guy is going to be equal to 2 cosine of 2t. So plugging that in, our y of t is now 8 e to the negative 3t minus 2 cosine of 2t plus the inverse of 6 over s squared plus 4. Now for this one, we want, it looks similar to this, which is going to be equal to k over s squared plus k squared. But we can see that our k squared is equal to 4, so our k is equal to 2. but we've got a 6 on top, so we're just gonna divide this by 3 in order to make this 2. But in order to do that, we're gonna have to multiply by 3 on the outside. So doing that, we end up with 6 times 1/3, but that's just equal to 2, and then s squared plus 4. And this is going to give us 3 sine of 2t. And that's it. Our final answer, y of t, is equal to 8 e to the negative 3t minus 2 cosine of 2t plus 3 sine of 2t. And that's our final answer. So, thanks for watching. That's the Laplace transform and how to use it to solve differential equations.